record this because we've got somebody out, and I'm not sure when they're going to be back, but we're really going to need this information. So the first thing I want to remind you about is just some standard definitions that you should already know. Work is the method by which you change something's energy. I talked about that on Friday. And in that discussion, I want to reiterate that work occurs whenever a force is used to cause a displacement. So we define work first as an integral, which is going to make some of you a little bit frustrated. But there's lots of pieces to this, so I think there's a lot here for all of you to share. I need to throw it out there that remember E&M comes after mechanics in almost every way. I mean, it builds on stuff people have already learned in mechanics. So a true course of physics would finish mechanics, have a short time probably talking about waves, maybe even some optics, and then you would launch into electricity and magnetism, with the assumption being that students have already covered enough information in mechanics to be able to apply information about work and energy. Now, for us, that's largely not true, because even if you've had a course in physics, most likely your definition of work ended with force and displacement, something like this. It wasn't an integral, and that's because in the conditions upon which you find yourself in AP Physics 1, the net force that acts on an object usually is a constant. So in those classes, we're more focused on the vector nature of the force and displacement rather than the integral nature. Now, we can't do that in this class, and part of the reason for that is we already have examples of forces that aren't uniform in nature. Meaning, one particle can apply a force to another particle, and the nature of that force is an inverse square. Meaning that if you have two particles in space, the force applied on one from the other gets smaller as the distance between them grows. So if I wanted to find out the work done on one particle by the other, can't use this because this assumes the force that's acting is constant the whole time. And that's just not true for most cases that we're going to start with. So we need a more robust way of talking about it, and the integral is the only way to do so. So for those of you who have not reached the integral portion of calculus, that should not affect what you will be able to do here. And for those of you who have, I'm expecting that you guys can acclimate to this fairly quickly. So if you've never had calculus, don't worry. I'm not going to have any expectation that you have to take the integral. But you do have to know what this entire statement means. And I see no reason why I can't count on that. First, let's start from the back. This still represents a displacement, or change in position. The D in front of it just means that it's small. So it's a small change in position. Don't forget the vector, because this means the direction of the displacement. That's critical because we're going to do a dot product here in a moment. This is the size of the applied force. And I want to be careful here. I'm going to say applied force, but that's probably an unnecessary word. It's the size of the force that acts on the object. But we will discover in mechanics that lots of forces can do work, and they can all be doing work at the same time. So the amount of work done is very dependent on which force you happen to be talking about. So you can have two objects doing work on an object, and the net work be zero, because at the end of the day, the object's energy didn't change. Consider just dragging a chair across the floor. You do work moving the chair, and friction does work taking that energy away. So at the end of the day, the chair's in a new location, but it has not acquired any kinetic energy. You drag that chair across a slick floor and you let go, the chair might keep going. Well, that's because you have successfully given the chair more energy. Your experience in work has to be broad enough to understand that all forces have the potential to do work. They don't necessarily add energy, they can also take energy away. Remember, work is the method by which an object's energy changes. Didn't say it would get energy. You just as easily take it away. So, size of the applied force. It's important to understand that this is the size of the applied force only over the displacement. So, if we're looking at small displacements, this is the amount of force that was applied for the specific displacement in question. Direction of the force. And here's where, those of you who are concerned, all this symbol means is to add up all the displacements. So it's like if you have to move your chair from where you're sitting now to the back of the classroom, but had to do it 1 centimeter at a time, then you could calculate the mini amounts of work, 1 centimeter at a time, going from where you are to the back of the classroom. The integral symbol just wants you to add up all of those. You see, work is a scalar. Because it's a scalar, you can add work together without caring about what direction or anything there is. So work can be positive, it can be negative, but it's a scalar quantity. Positive work increases the energy of the object. Negative work takes that away. Now, it is appropriate this time, though, that we talk about this. This is called the dot product, or scalar product. There are 2 ways to multiply vectors together. Your experience should be that you have those 2 ways already kind of in your lexicon, but you might not. The dot product produces a scalar as the answer. The cross product produces a vector for the answer. So when you multiply vectors together, you have to be conscious of what your goal is for that particular product. Dot products will result in a scalar for their answer. And the dot product is very specific. It is the amount, in this case, the work done is based on the amount of force in the direction of motion. A scalar product is looking for how much of one vector is in the direction of the other. That's what a scalar product does. It looks for how much of one vector is in the direction of the other. Now, that's an easy thing to say. It can be harder in practice. But again, the scalar product is how much of the one vector is in the direction of the other. Now, I believe that this isn't a particularly challenging thing to understand, meaning when we calculate work, a force that does work has to be responsible for the motion of the object, either trying to move it in the direction it's trying to go or trying to prevent it from moving. So there has to be a component of that force in the direction of motion, or it doesn't do work. Again, that's a definition from last year, but I'm hoping that's not hard for you to remember, that only forces that contribute to the motion of the object can actually be said to be doing work. The dot product is testing for that circumstance. So to not make this too terribly hard, now getting back to this for just a minute, there is nothing wrong, if you need to, with rewriting this as f dot dx dot cosine theta. But be careful here. You can't assume that the angle is constant. You have to test each of those variables out before you determine whether you can take this and turn it from an integral into just a product. If any of those are changing over the interval, it has to be integrated. So a lot of people don't have an example. So those are all the parts of the definition of work. I'm hoping that was a quick refresh of what you should already know. Are there any questions about these pieces? Yes, ma'am.
Sorry, for the example that you just showed, that would be
From an integration to a non-integration, only if the force and the angle do not change with the displacement.
things.
Because the displacement is the one that has the d in front of it, it's the one that dictates what other variables have to stay constant. So over the interval, if the force is changing or the angle is changing or both, you have to integrate. Which again means break it up into pieces and sum across the interval. Now, luckily for us, you don't have to really do much assembling. A fixed equation like this has already assembled the integral for you. You have to act on it, but you don't have to assemble it. It's not like the other stuff we're talking about where you have to assemble the integral. This one is already assembled. Yes, sir?
So you said the dot product is like how much of one vector like works in the direction of another?
Yes, sir.
So what, like, I don't understand like why you f times dx times cosine theta. Like, what's the like reasoning behind using those measurements and multiplying them?
What's the reason that we would use force and displacement in calculating work?
Well, no, just in dot products, like I was just like confused on like why it works that way. Like why multiplying those together would show you how much like of one force is in that direction.
Okay, if that was the takeaway, then that was the wrong thing to take away.
No, I understand like how like you like why you use that for work, but I just don't understand why it works.
Okay, yeah, but what I want to say first is the dot product doesn't show you how much of one vector is in the direction of the other. That's not what the dot product does.
Okay.
The dot product requires one vector to be in the direction of the other for the product to exist.
Okay.
So, but it doesn't tell you how much is in the direction. The angle tells you how much is in the direction of the other. But the dot product is, I'm trying to think if there's a general answer to that, like that what's something that all dot products share. And I don't know that I have one, interestingly enough. Like, why is the product of a vector required to go through either the dot or cross product? I don't know if I have a good answer here. I know what I think the answer is. I hate to speak to it because it's conjecture. But if I was to conjecture, I would say that the creation of the dot and cross product were weren't a pure math structure. That they were created in the fact that there was a certain usefulness for the outcome of the product. So, with that being said, like a good example of the cross product or the vector product is torque. So in computing how hard you twist or turn something, you have to push on something to get the door to turn. That's my example in class every year. And to get the door to turn, you decide where on the door you want to apply that force and then how much force you want to apply. But those are easy to kind of think about, but then there's the angle of the force you apply relative to the door. It's most effective to open the door by pushing straight ahead on the door and applying it at a right angle. So we know from experience and practice and observation that forces that are perpendicular to the torque arm are more effective. So was the cross product created in an effort to demonstrate that? Did we say, okay, we know that we need, the force to be perpendicular, so we're going to use the sign as our method for determining how much of the force is actually acting to open the door and how much of the force is wasted because it's going into the pivot? Was that, I mean, we created the cross product to do that and then develop vector mathematics outside of that? That I don't know. That's my conjecture though, is that when, and this is not a purely Newtonian idea, but the idea of energy and work is something that developed. And we know that when Newton was trying to put together a concept of energy, his definition of work was based on force, which was his whole impetus for regenerating an idea of physics. So my argument would be that, and this is pure conjecture, that he knew that only the part of the force that was acting to cause motion or impede motion was the interface by which the energy was being delivered to the object. And so he needed a method for measuring that. And I don't know whether he pulled the dot product off the shelf and it already existed, or whether he generated a form of mathematics in using these vectors to create this new product, the scalar, of work. I don't have that answer. It'd be interesting.
Yeah, I mean, I remember like when I was like in pre-calc, like we used the cross product to find the volume of like 3D shapes that were made up of those vectors, like parallelograms or stuff. So,
Right.
But funny enough, I don't remember how dot product works. So I was just wondering.
It might be an interesting lookup. I'm sure Wikipedia would give me some starting points on it. But I bet if you looked up dot product in Wikipedia, that'd be a long entry.
Yeah.
So, people, how many of you like Wikipedia?
It's actually.
Oh, I love Wikipedia, yeah.
Yeah, it's fun.
It's a great starting off point for so many things. And, something like this would probably have a pretty interesting entry. Or it'd be completely boring. I mean, it's possible. It had nothing there. So every once in a while I've gotten into Wikipedia just because, you click on something, don't understand what the meaning is, and you start diving down that rabbit hole, and a couple hours have passed. I find it a little bit better than surfing the internet now because at least when you're going across Wikipedia, it feels like you're gaining something. A lot of times I'm surfing the internet, I can't find any of the things I'm looking for anymore. I don't know about you guys, but I'm trying to build something right now, and I'm having a ridiculously hard time finding anything on the internet. I thought it'd be all over the place, and there's not a thing out there. Yeah.
My brother, who works at Google, said that Google's search engine has become less about trying to let people find what they actually want and more about getting money from companies that pay to be on the search engine. So it's harder to now search for things.
I keep being told that you kids are so knowledgeable about stuff when it comes to tech things, but let's be honest, you are just not. So
It's a pretty low
it cracks me up though that all these teachers here think you guys know everything there is to know about techie stuff,
It's a pretty low bar.
but you just don't. So, but again, good to know. So let's take a quick look at what my expectations are going to be here when it comes to transitioning us from discussing work in the mechanics world and how it's going to have to be kind of played out discussing work in the electronics world. Because there are going to be some issues going forward, things that might be different. And one reason why we don't talk about energy the same way in electronics as we do in mechanics. When we deal with electric fields, they can be shaped in ways that are complicated. And more importantly, we know that the way in which an object experiences a force is by its interaction with the electric field. That is the model that we're using. So a point particle in this region of space will experience a force in the direction of the field, assuming that the point particle is positive. So if I have just some particle in space and I tell you that it's positive, the size of the force it experiences will be equal to the product of the charge times the size of the electric field. Now, that shouldn't be a huge deal. We've kind of talked about that. When we can, just a minute, if that's okay. If I release this particle, positive work will be done by the field. Is there no doubt about that? The field will push the particle to the right, the particle will go to the right. We are going to have to be careful though, because what would we say is the kind of work done on the negative particle? the field will push on this particle to the left, and it will move to the left. Does that mean that negative work was done on the particle by the field? You do understand why we are going to probably have to come up with some convention to help us understand whether positive or negative work is being done when we move particles with or against a field. A convention that will be consistent. It's a complication that makes it harder than gravity. Okay. Comparing that conversation with a conversation that also includes, say, gravity. You know, we've known from dealing with stuff last year that if you have an object with mass and you lift it up, that you have to do work on the object to lift it away from the ground. And this, again, not a surprise, the work would be equivalent to the size of the force you have to apply, times the change in position, times the cosine of the angle, all those things that we remember from last year. It all resulted in the amount of work being done equal to mgh. Yeah?
Oh, are you going to be erasing this one too? Or should we?
I'm going to be flipping back and forth between these two screens.
Okay, thank you.
Sorry. I guess I could have said that a moment ago.
Yeah, that would have been a little helpful.
But I'm gonna, so in this instance, the gravitational field is directed downwards. We would call that the acceleration of gravity, but again, the gravitational field is this way. We do work against the field, and we said last year that doing work against this field would store that energy as gravitational potential energy in our object. So we brought our object here, some distance h, and this object acquired gravitational potential energy. In most discussions, we didn't really sit around worrying too much about sign, like whether this was positive or negative, or whether the object's energy increased or decreased. We just kind of said it now had potential energy, and we knew that was important because we could release the rock, and the rock could then convert that potential energy into kinetic energy. Sound familiar from last year? But the truth is, there were two forces doing work on the rock while we were lifting it. That's why when the rock got to this height, it wasn't moving anymore. There's the fact that you did work lifting the rock, but at the same time, gravity was pulling down on the rock, and it was also doing work on the rock. You did positive work, gravity did negative work. Based on the direction of the field, the direction of your force, and the direction of the displacement. The lifting of the rock involved two different forces doing work. Good so far? So, truthfully, there was positive work done by you and negative work done by gravity. When that's true, but a simple example would just be if you pull a box using a pulley. So there's a pulley up here, and it's connecting the box to, say, a person. This is actually a ridiculously hard question to figure out how much work is done on the box. It seems like it should be easy, except that if the person applies a constant force, even if the force is the tension here, the angle between the box and the cable is constantly changing. So you can't figure out the amount of work done by just doing simple force times distance times the cosine of the angle between them, because as the box gets closer, that force is being less useful in moving the box forward and more useful in lifting the box up. This is actually a ridiculously hard question if you factor in the fact that the normal force is responsible for the frictional force. You start looking at a problem like this, and it can make you unhappy very, very quickly. So this has never been asked in the AP exam in mechanics, but it would be a pretty interesting question, even if it's just qualitative. You know, the person probably would find that it's much harder to move the box when it's closer to the pulley than when it's farther away, even though it's reducing the friction a lot. It's just that you have so less force going in the direction of motion. But again, interesting, like, qualitative question, but probably not one that you ever want to actually have to face in your homework. So, I gave this an AP1 though, as a qualitative question. It's a good qualitative question in AP1. So you guys who take AP1, there's nothing wrong with being able to explain these parts. But to actually have to do the math for it, oof, brutal. Just brutal.
Example of how you can't have everything inside the interval.
This would be one where, yeah, this one is one where I would have to integrate, because all three of the variables potentially are changing as the box moves across the floor. So you're able to go, let's use the example that you guys are already pretty familiar with. Trying to slide something across the ground. If you're pulling on the object and you pull with a force that's in this direction, and you know that there's some form of sliding friction acting on the box while it's moving in, say, this direction. So maybe a tension or something is the green arrow and friction is the blue arrow. Is that good enough for you guys, especially you guys with maybe a little minimal experience, understand that those two forces can act on an object? If the object were to be displaced some distance to the left, then the vector for displacement would be this way.
Sure.
Yeah.
I'm not sure if I remember correctly, but wasn't there like a cosine in the work?
I'm trying to get there.
Okay.
Don't worry. We'll get your cosine in just a minute. Okay? So if x represents the direction of the displacement, then you're trying to use the dot product to indicate how much of each of these forces has to be in the direction of the motion. So delta x establishes the direction of motion. And the dot product tests to see how much of each force is in that direction. So as it's been pointed out, that's trig. And that's exactly trig. That's what the dot product does. The dot product tests for how much of one force is in the direction of another. That's what trig does. So we'll need to have this angle in order to test the size of that force. And which component do we want? We want the component that is adjacent to that angle, because that's along the direction of x. So it is true that if you have f dot dx, one way to find the dot product is to know the angle between the two vectors and compute the cosine. Now, I'm trying to say that clearly because there's other ways to write vectors. And because there's other ways to write vectors, you don't always know the angle between them. There is a version of the dot product that uses the rectangular coordinates of vectors and allows for you to compute the dot product without converting to polar. It involves a little bit of matrix mathematics. So those of you familiar with matrices know that there's a way to express a vector in a matrix, and you can use a determinant of a matrix to determine a dot and cross product. But most of the time my students are unfamiliar with matrix mathematics. I'm not sure it's being taught very much anymore. It's not being taught in pre-calc any longer. Is it being taught at all in calculus AB? Anybody at all interested in computer programming? I would encourage you guys to spend a little bit of time looking at matrices. and understanding a little bit of matrix manipulation, even if you have to do it on your own. Most all advanced programming at this point really is a study of matrix manipulation, because almost all data structures are matrices of some form. All three-dimensional graphics programs, especially gaming programs, store graphics information in a matrix and use matrix manipulation in manipulating the view of the world that you have in your first person or even side scrollers anymore are using them pretty advanced, like, because most side scrollers are based on a 3D engine. So if you have any interest, I would encourage you to look into it. If there's anything that should be should be learned here, is that there's a lot of math we're not teaching in favor of nailing some more basic concepts. And so we're having some losses, is what I'm noticing in schools, and matrices are one of them. It was, when I first moved here, kids were getting basic matrix information, and now it's completely gone. You can solve every linear equation using matrices without ever having to do substitution. That's how you get a computer to solve linear equations. And you don't have to stop at 2 or 3. Using a matrix, because it's just doing the determinant, you can solve a system of 50 linear equations almost as easily as you can solve 2 or 3. Kramer's rules allow for it, and it's really pretty straightforward. So if you've never learned Kramer's rules, it might be worth it as a fun exercise someday to take an aside and learn Kramer's rules. You'll never need them for the AP exam. It's just something that's interesting to know. So I think you guys are stuck with what? Probably I think all you guys ever do is elimination or substitution now, right? You don't do row echelon mathematics at all. So there's just a lot more math out there. You guys, you mathletes know what I'm talking about. There's always more math to know. All right, so this is a way of taking the dot product by just using the cosine, and that's the predominant way we will use. I'm not trying to make this any more complicated than that, and I'm glad you brought it up. But I like to explain where the dot product comes from, because we will be talking about the cross product, and getting them together, understanding the nature of why you use one over the other is important. The answer here is going to leave you with something that is a scalar, but more importantly, we're looking for how the two vectors are related. It's appropriate to understand here too that in this particular picture, the green arrow's contribution to the work would be positive, because the angle is less than 90 degrees, while the blue arrow's contribution will be negative. The sign of the cosine determines whether energy is being added to the system or taken away from the system. So the angle for friction is going to be 180 degrees. So you would compute the work done, but you'd have to do the cosine of 180, which is going to give you -1. But even somebody else, just pulling at this angle would be a force that would be at an angle greater than 90 degrees, and therefore will produce a negative from the cosine function. So it is the cosine function that determines whether energy is being added or taken away from the system. It's the way it's mathematically determined.